Well, hello. Welcome to the next to last lecture in this course. And like all lectures this week, this is going to be more a survey of a range of work that I and my collaborators have done. But it does display to you what can be done using the computational tools that we have discussed this semester. Now, the topic today will be climate change policy, so it's a topic also of some interest. If I had had really good foresight, we would have done work on this about epidemics. But anyway, you can't predict everything. But at the time we started this, the popular thing for research was to do climate change things. Or I say popular, or what I really mean is that the kind of work that could get financing was on climate change. Now, do you see the front page of my first page of the slides? That's what you should see now.
Yes.
Good, thank you. Now, so what we're going to talk about is optimal carbon policy with business cycle and climate risks. And by the way, all of this work is joint with Young-Yang Kai and Thomas Lonchek. And I also sent out a paper that was joint with Carl and Alina Miftakova. And if I have time, I'll point out what we did there and to show how the direction in which we're going. Now, so everybody agrees that CO2 concentrations are rising. Okay. Now, not everybody agrees about what should be done. So what Young-Yang and Thomas and I did is we built a dynamic and stochastic integrated framework for models of the climate and the economy, and we called it DSICE. Now, the canonical model in this literature is DICE. This is a model that was first presented by Bill Nordhaus in the early 90s, and it stood for Dynamic Integrated Model of Climate and the Economy. And so we want to give our names something closely related, and we had two choices, SDICE and DSICE. And Thomas said that he laughed when I said DSICE because then he joked about how some Germans might mispronounce it a bit, and I said, bingo, we're going to stay with DSICE. So, and the whole point is to take the key elements in this canonical model from Nordhaus, basically for which he won a Nobel Prize, but that was, we didn't know that at the time we started this in 2000, I don't know, 8 or 9. And what we want to do is add economic risk to the model. His model, as you'll see, had deterministic economics and deterministic climate model. And neither one of those is an accurate portrayal of either the climate or the economy. And so what we want to do is add in uncertainty in growth rates, economic growth rates. And in the early 2000s, there was a set of papers that came out and said that economic growth the growth rate is close to a unit root. The growth rate is close to being a random walk. Now, what does that mean? That means if you have a spurt of positive growth this year, then you probably have positive growth next year, somewhat smaller, and then but you'll have a positive growth for many years into the future. What this does is that this means that this dramatically increases the uncertainty about economic productivity going into the future. Now, the other thing that we did is that Nordhaus, of course, writing in the early 2000s, he had a standard time separable utility function. But also, we knew by that time that if you have risk in your problem, that additively separable utility functions are not good. And this is the risk premium puzzle due to Prescott and Mera observing that point. Now then, so much of the literature has moved to the Epstein-Zinn class of preferences, which do better in terms of representing attitudes towards risk. And now, if there's anything risky in the world, it certainly is this whole climate business. We don't know what's going to happen on the economic side. There's risks on the climate side. So we should put in preferences over outcomes that are consistent with the observed attitudes towards risk. And whereby observed, I mean the attitudes towards risk that are displayed in decisions made by people, in particular their asset allocation choices. Now, economic risk, fine. Now, climate risk. Now, in many ways, there's enormous risks. Now, now, at a deep philosophical level, you know, the climate equations are basically Newtonian physics. And so you might say, well, they are deterministic. And now, of course, you go even deeper, you get into quantum stuff. But the thing is that whatever your view is on quantum or Newtonian physics, the fact is that the best way for us to think about the evolution of the climate is that there is a lot of uncertainty. Perhaps the climate is following a deterministic path, but we don't know what that path is, and we do not have the capacity to predict exactly where things are going to go. And so instead, we have to realize that, well, there's a lot of uncertainty about where things go. And by the way, the equations of the climate are a big component of it is fluid equations, which then lead to chaotic kinds of behavior. So it's very natural to view the climate process itself as being a source of stochastic evolution. Now, so there's a lot of things about the climate we don't understand, and it's the way we talk about the way we do when we don't understand something. What we do is we attach probabilities to alternative events. Now, some climate events. Now, the main focus of the climate literature is on the increase in temperature. Increase the temperature, and then the output of agriculture will fall in many parts of the world. You know, increased CO2, increased temperature, maybe the Ukrainians and the Canadians will love that. But, so there's distributional aspects, but generally significant increase in temperature will reduce agricultural productivity. Now, some climate events are not as gradual as that, not as smooth, not as proportionate. Things, for example, like the glaciers melting. Now, we do know that some glaciers are melting. Now, whether it is just natural variation or induced by the extra CO2 in the atmosphere, I'm not going to get into that. But it's natural to think of glaciers melting as, you see, the thing about a glacier is that once it's melted, it's melted. See, the thing with agriculture is that temperature goes up, agricultural productivity goes down, but then if you get the temperature down, well, then your agricultural productivity goes back to what it was. With glaciers, if you have some decades that are warm, and that leads to the glaciers melting, and then you get the world's temperature down, the glaciers do not magically appear. They may over thousands and thousands of years. You have to remember that these glaciers are the accumulations of thousands of years of snow and ice. And so glaciers melting is a different kind of event. And now, why do we care about glaciers? Well, okay, not many people do. But then when you tell people that their oceanside homes will be flooded, then they start caring. And so the issue is with the glaciers melting, will that raise sea level? And now people are going to care. Now then there's the thermohaline circulation collapse. The THC is the flow of warm water from basically around Florida that then goes up the Atlantic coast of the US and then goes over towards Europe and then bathes England in a warm flow of water. Now, by the way, and you might say, well, there's no warm water around England. Well, the thing is that the water is warmer with this flow than it would be otherwise. And this flow of warm water makes the climate in England and Northern Europe, let's say Northern France, more temperate than it would be otherwise. Now, warming could possibly stop that flow, could interfere with the thermohaline circulation. And in that case, global warming would lead to a cold England and a cold Northern France and other parts of Northern Europe. So you put all these things together, glaciers melting and thermohaline collapse, you're going to have a cold and wet London and a cold and wet Northern France. And in fact, I think if all the glaciers in the world melt, Paris will still be inland, but the distance between it and the English Channel will be reduced by a factor about 2/3. So these are the reasons why people are thinking about these things and care. Now, there's a lot of things we don't know. We don't know what the right models are. Even if we know the right model, we don't know what the right parameters are. So there's an enormous amount of uncertainty involved in this. Now, so what we do is we take this simple model of Nordhaus, which many people have used and generalized in many ways, but we were the first to actually put in uncertainty. We weren't the first to get something published, but we were the first to put in, because this work goes back to 2011, put in a business cycle. Actually, we still are the only one to really put in a specification for stochastic productivity process that is predicted by the data. Other people cheat by having a much less variable productivity. What we do, we find a variety of things. Social cost of carbon. Okay, it's a price, so it's got to follow a random walk in a stochastic model. It turns out that the variance of it increases greatly over time. So we really have little idea about what the social cost of carbon or what the optimal carbon tax would be in 2100. Now, the other thing that people like to talk about is they argue over what the discount rate should be. So let's say global warming is going to create damages, but some damages are going to happen sooner than others. So the argument is, okay, what discount rate should we use to value greenhouse gas policies? Now, so then you get this argument over, should the discount rate be 1% or a fraction of a percent, which is what Stern argues, or should it be based on market rates on assets, which is the approach that Nordhaus uses? And so you get this argument. Now, the problem is this argument comes in the context of basically a deterministic model in the back of their mind. Now, however, we know from financial economics that when you have a cash flow stream, there is no one discount rate that applies to all streams of cash. That we know from consumption cap M theory that the rate at which you discount a stochastic flow of cash is related to its correlation or its covariance with the aggregate endowment. And so different kinds of damages will probably have to be discounted at different rates. And this is a paper, the only paper I know of, which makes that point inside an fully specified model. And we'll see what the implications are. And in particular, what we find is that the damage is due to what we call tipping events. Those are the things that are irreversible. Once a glacier melts, you can't unmelt it. Though the damages from those things should be discounted at a much lower rate, because basically those damages are not as cyclical as others. So what we're trying to do is combine the best macro models with the canonical models in the that can be applied to economics. Now, by the way, we are not using the enormous models that the climate scientists are using. These are the models they use for climate are enormous models requiring maybe even days of supercomputer time. And these models try to calculate the impact of CO2 on precipitation, on temperature in many parts of the world, on ocean, the ocean. Now we cannot ever, certainly in my lifetime, incorporate economics into those models. And the reason is very simple. In the Newtonian physics, the differential equations or partial differential equations are what we call initial value problems. You specify the initial state of the world or state of the climate and the ocean, and then you turn on the partial differential equations, and then everything evolves over time. Economics is not an initial value problem, because economic decisions today depend on what the economic agents think is going to happen in the future. And so when we write down, let's say, a simple finite horizon life cycle problem, we don't have just a basic initial value problem. We have a 2-point boundary value problem. Not what matters is initial wealth. What matters also is terminal wealth. What a requirement, for example, that you not die in debt. So we have a 2-point boundary value problem. Now, you incorporate economics, even the most trivial economic model that is of the modern sort, all of a sudden, the whole system becomes a 2-point boundary value problem. So there's no way that those enormous climate models that the climate scientists use can add in economics of a modern form. What some people do is they add in an old-fashioned economics model called myopic models, where people make decisions only based on the conditions today, and then the dynamics are based on some simple interest rate rule. But now that stuff was, basically banished out of economics 40 years ago, because we know that expectations matter. We know that rational expectations or rational beliefs, some form of rationality, best describes what people do. We also know that many of the actors making decisions, such as the big oil companies, such as the energy generation firms, they literally do look at multiple decades of expectations of what's going to be the case. So if you can't, a myopic model is ridiculously simplified, so and unrealistic. And so then adding economics to this means you have to simplify the climate side. And that is Nordhaus, as part of Nordhaus's contribution, in consultation with Steven Schneider, came up with a combination of climate and economics that is tractable when you put them together. Now, what is the current state of integrated assessment modeling? Now, actually, most of the integrated assessment modeling, the models that add economics to climate, most of them are of the myopic expectations form. Now, if you look at the academic literature, you will find papers like Nordhaus, simple climate but perfect foresight. Now, if you leave the sort of narrow academic literature, what you will find is an enormous amount of, well, these people have their own journals, but their stuff is not publishable in mainstream economics journals, but in field journals and their own climate journals. You have this army of people with substantial funding from DOE and EPA that write up these multi-sector models and have some climate, but then they do the myopic expectations. So these models from 30 plus years ago, from 40 years ago. I guess I've been talking about this stuff for 10 years now. I got to add on 10 to that 30. So basically, a lot of the work that's out there is just not acceptable by modern economic standards. And even if you're a new Keynesian, you would say this is not acceptable. This is not a matter of Keynesian versus Chicago type religious fights. But no, what these guys are doing is not acceptable even to a new Keynesian kind of guy. Now, the climate science, the hardcore climate science guys, they use the best algorithms available, the best hardware, but economists, even these guys, these myopic guys, they just use laptops. Now, also the economists, when the economists are in charge of computation, things often don't go too well. The Interagency Working Group in the US government issued a report in 2010 that it was a report on what the social cost of carbon was, what the optimal carbon tax would be. And they used a simple model. Basically, they took Nordhaus's model to get an estimate of this. Now, in a paper that I sent out to you, we pointed out, because we actually looked at the code that was used, and we found out that there was that the differential equation they used that was discretized in a very strange way, implying that CO2 from 10 years in the future is already warming the Earth today. Kind of weird. By the way, this fact is in the code, not in any document, not in any paper or any book, but in the code. So the code can be different from the equations. So you have to look at the code to know what's really going on. We noticed that and we said, well, this business of trying to solve a differential equation, which is what's really going on, by discretizing at 10-year intervals, doesn't sound right. So then we basically did the differential equations at annual time periods, and even we could do it down to monthly. And what we show is that when you do the differential equations correctly, their social cost of carbon numbers were significantly higher than what they should have been. So now, so that was a case where we had the code and we could actually check it. Many people in this business of taking money from DOE and writing up tons of papers, which don't get published in highly ranked journals, they don't post a code. And in fact, particularly, there's a project at MIT many years ago that had a paper in science. And I asked them, could they send me the equations that underlay their economics model. I asked for the equations, not the code. People get a little bit touchy about code because they say, well, the code is my code and all that. I don't want to give that away. So I asked for the equations. The response I got was, oh, Ken, nowadays software is so good that we never have to write down the equations. Well, anyway, there was a variety of emails back and forth, back and forth, back and forth. And eventually this MIT project did decide to send out their code and post it publicly, which is what I demanded. And then a friend of mine tried to run the code and it didn't work. So there's real problems in the integrated assessment modeling part because, it's not open science. And there's a big lack of openness, which is one reason why you don't see more of this work done in sort of mainstream economic journals, because it's not that journals require posting of the code. They may say they do, but they don't really. Or you can post some unintelligible mishmash of garbage and they're happy. But journals do not like it if you refuse to actually tell the readers, or refuse to tell the readers, what are the demand curves and what are the parameter values for demand and supply curves that you use. That much is expected. And these guys will not do this. The US government won't do it either. So that's a problem. Now, my views on where the integrated assessment modeling community should go was written up in a couple of proposals and projects. And basically, what the goal of these projects was to create an environment for economic modeling and simulation, an environment, not just one model, but an environment, and open source tools, and to create a framework, not just one single model, but a framework wherein you could specify your own model and then push a button and then see what the implications are. And we also incorporate uncertainties and risks. And we got some money from MacArthur Foundation. Then we decided to go bigger. We added variety of people, in particular Lars Hansen and Todd Munson, to this project. Also, we added in Buzz Brock, who's doing very nice work in this area. And also, I managed to insert into the proposal language which meant also that we were going to be able to do dynamic scoring, which means analyze the impact of changes in tax policy on the economy. And I was very pleased with how everybody thought my point. I had a good point. I said, you cannot really understand the impact of a carbon tax on an economy unless you also understand what the other taxes are doing to resource allocation. And so therefore, if you're going to write down a good, reliable model that could talk about carbon taxes, you should also have one that has income taxes, corporate income tax, personal income tax, and other taxes in the model. And they said, fine, oh, good idea, good idea. So basically the goal of these projects was to build modern computational tools for economic modeling, basically do for modelers in economics working in this area for what TSP, RATS, and a variety of other software packages have done for people doing empirical work. With empirical work, you write down your specification, what the variable is on the left-hand side and what the variables are on the right-hand side, and you push a button and then it reads the data and then spits out the point estimates, coefficients, standard errors, et cetera, et cetera. And if you have to do a 2-stage least squares, it'll do that for you. If you do 3-stage, it'll do that for you too. So basically, econometrics packages were an enormous boon to empirical work because the person doing the empirical work did not have to write the code to do the regressions or anything else. They just fed it the data and the model, and out comes the results. And that's what we were trying to do for directly integrated assessment modeling, but also economics more generally. Now, the other goal of this project was to incorporate the insights and objectives of something called validation, verification, and uncertainty quantification. Now, what do they, the thing is that everybody understands that, by everybody, I mean, any scientist understands, and particularly any engineer understands that the models they have are not perfect. And you don't necessarily have the right model. You don't necessarily have the right parameters, even if you have the right model. So, and this is something that, despite what economists may think, this also is the case for applied physicists and engineers doing a variety of work. And so they have put together a sort of collection of practices which come under the umbrella of validation, verification, and uncertainty quantification, VVUQ. What do they stand for? Validation is the model that you're using true? Now, this is econometrics in the case of economics. This is something that I'm not going to say anything more on, but we understand what that is. Verification is the code that you wrote down solving the model that you specified. Now, when I say code, I mean all the numerical details. You have a differential equation and you want to discretize it somehow, are using the appropriate discretization procedure. If you're doing an integral and you're doing Monte Carlo sampling, are you taking enough samples to get the right answer? So that's verification. Now, by the way, this is when I talk about this, I add the phrase, "Doverine no proverne," which of course horribly pronounced Russian, but trust but verify. And that is the attitude within the VVUQ literature. Now, uncertainty quantification is how much do the results depend on your beliefs about the parameters? So that's uncertainty quantification. Economics would call it sensitivity analysis. So that's now we're familiar with some of these things, but these people have combined all of this into this VVUQ framework, which is very useful. Now, so what we did is we built on the Nordhaus DICE model because it is the one everybody knows about and uses, and so it's a common thing to build on. Now, is it the absolute truth? No, of course not. There's a lot wrong with it, but there's a lot wrong. But it is the platform that people use to discuss these issues. And everybody understands its weaknesses, but it still is useful to see, well, within this model, which has this certain set of interactions, what is likely to happen? And also, it's natural for us to add uncertainty in economics and uncertainty in the climate to this. Here is a picture. I generally hate pictures. And then one of my I think it was Thomas, decided to, despite my protestations about hating pictures, he came up with this picture, which is very nice in terms of describing what's going on in DICE and also in our stochastic version. DICE is basically the solid arrows. And then the DICE is basically the black arrows. And then the blue is our stuff. So the economy emits CO2. It goes into the atmosphere. Now, the extra CO2 in the atmosphere warms up the atmosphere. But the CO2 in the atmosphere some of it gets absorbed into the upper ocean. And once it's in the upper ocean, sometimes part of it gets absorbed into the deep ocean. And then there's this gas diffusion going on between the atmosphere and these two layers of the ocean. Now then what's happening also is that the CO2 is warming the atmosphere, but then a warmer atmosphere is increasing the temperature of the ocean. And I suspect it's the temperature of the upper ocean. And so there again, you have heat diffusion. So here you have gas diffusion going on, here you have heat diffusion going on. And then the temperature of the atmosphere is what does damage to the economy. Now one might say, well, if we include fishing and all that, temperature of the ocean is going to do that also, but the DICE model and what we do focuses just on how the atmospheric temperature then affects the economy, reducing productivity of agriculture, increasing heat, increasing temperatures, so you have to use more air conditioning, et cetera. Now, what do we add? Oh, and then by the way, there's the other thing that Nordhaus adds is mitigation. What you do is you spend money to reduce the amount of emissions. So by spending money, you can reduce the amount of CO2 that gets in the atmosphere. For example, if you have a coal-fired electricity plant, mitigation would be sucking some CO2 out of the exhaust and then hiding it somewhere. Mitigation. And then also from all of this in the economy comes consumption and utility. Now, what did we add? We added stochastic growth to the economy. Nordhaus specified a deterministic growth rate in productivity, and we added a stochastic component to it. And then now what we also did is we added a stochastic component to the temperature. The temperature increases the probability of bad stuff happening. And that's what we've added here. So that's an overview of what we do. Now, here, what we have here are some of the equations that model this. We have carbon concentration is, okay. Okay, the question is, let me talk about that at the after the lecture. Now, carbon concentration, you have 3 layers of carbon, the atmosphere, upper ocean and lower ocean. And then of course, the law of motion is just, you have this matrix that mixes up the concentrations amongst the 3, and then you have the atmospheric CO2 is getting extra emissions. Now, emissions are not going into the ocean at all, so you have this source term. Temperature is similar. You have two temperatures to keep track of. And then you have temperature tomorrow is again, has this diffusion aspect. Basically, if left alone, the temperature is going to move, the temperature gap is going to be reduced between the ocean and the atmosphere. And then you have a source term that basically the temperature of the ocean is not going to be immediately impacted by anything, but the temperature of the atmosphere will be impacted by the carbon concentration. So this is carbon concentration of the atmosphere. One of the state variables up here does affect forcing, which does radiative forcing, which then does increase the temperature of the atmosphere. Now, one innovation we have here is the tipping state, the innovation of DSICE. Now, what we say is that there's another state variable, basically representing the state. Let's say the example we have, the state of a glacier. So maybe the glacier is in good shape. It's holding its own. Maybe there's a little melting, but it's also getting refreshed by new snow. And so that's the state, in a good state. However, what may happen is that with enough warmth that generates enough melting that the glacier will hit a tipping point and then stochastically, according to a Markov process, gradually lose its ice and disappear. Now, the disappearance of that, the glacier disappears, and then you have a change in the state of the glaciers, and that may raise the ocean levels, and that's going to also damage the economy. So so basically, if the glacier is in perfect shape, this J is a 0, and then but then as things get worse and oceans rise, then this J will rise to some level, not 1, of course. And so basically, this is called the damage factor. Now, this is basically net of damage output. Basically, output is going to equal the regular output multiplied by this. And so an increase in J as well as an increase in temperature will damage the economic output. And here's the economic system. Basically, we have Cobb-Douglas production function. There's a deterministic trend for productivity. However, that stochastic process, the deterministic trend is multiplied by a long-run risk process. And so here is the production function, and the productivity parameter is going to evolve over time. And then the output, total output at any point in time, is going to be what the production function says if there is no damage from the climate, multiplied by some factor from the climate that reduces output. So that's the model. And then we have a capital stock equation like this. Now, what happens here is that output is split between consumption, investment, and mitigation expenditure. Mitigation expenditure, capital psi t, is mu is the emission control. Mu is the percentage of emissions that you prevent. So emissions is going to be from an industry is going to be some parameter, some carbon intensity of output parameter multiplied by 1 minus mu. If mu is 1, then you have stopped all emissions. If mu is 0, then you aren't doing anything. And so emissions is proportional to output, but then this is the cost of emissions. So if you increase mu, your cost of that in terms of dollars, taken out of output, is going to be this function of mu. And this is going to be convex, so this theta 2 is greater than 1. So it's a convex cost. Economic policy evaluation. What we do now is we say that there's a social planner that's choosing aggregate consumption, aggregate labor supply. Labor supply is basically exogenous here. Basically, population, labor supply equals population, and population grows on some deterministic path. But the planner does get to choose consumption, chooses how much money, how much of the output goes into investing in capital stock, and how much goes into mitigation. Now then, so this is utility is expressed in this fashion. Your utility, this is the Epstein-Zinn recursive utility formulation. Utility and utils, and this is basically sort of a dollar unit version of utility. You have today's utility flow plus then this dynamic Epstein-Zinn aggregator that allows you to distinguish between intertemporal elasticity of substitution and the risk aversion parameter. Remember, the evidence from the empirical evidence is that intertemporal elasticity of substitution is moderate. It's not a low number. It's moderate number. Risk aversion, however, appears to be very high. Now, when you have separable utility, you're assuming that risk aversion is the inverse of intertemporal elasticity of substitution, and that leads to the equity risk premium puzzle. But what we do is use the Epstein-Zinn formulation. We change around things and we come up with this value function expression. So this is just dynamic programming. You're maximizing utility today plus discounting of some dynamic aggregator over the value function output tomorrow. Basically what happens is that tomorrow's value is a stochastic variable, and then you give it a nonlinear, you give it a either concave or convex twist, and then that random variable, you take its expectation, and then you do basically unwind that twist. And here's the capital stock tomorrow is undepreciated capital plus output minus consumption minus mitigation expenditures. And here's your climate equations. And here's your process for the long run risk process. It has two states. And then here's your climate state. So this problem is a dynamic programming problem with 9 states: 1 capital stock, 3 carbon concentrations, 2 temperatures, and then 3 climate, 2 productivity process, and 1 climate state. And you have 2 control variables. And what we did is we solved this problem over a 600-year horizon, annual time steps. The terminal value function we set to be at 600 years to be, we basically say, okay, at this point in time, everything's the same. The temperature in the ocean, everything in oceans and atmosphere and all productivity is the same. We can then compute what we did. That pins down year 600 value function. And by the way, since you're discounting over 600 years, it's not going to matter. Now, where do we get the gamma and psi numbers here? Well, we go to the macro literature, and these various guys within the last 20 years have come up with a variety of numbers. And of course, it's a variety of numbers. Everybody has to come up with their own numbers. And so we basically used these estimates as the range of gammas and risk aversions that we're going to look at. Now, the key thing to point out is that the way DSICE is set up is that it really is geared to solve a difference equation in a Banach space. And that's what this is. It's a difference equation in a Banach space. By Banach space here, I mean, okay, you're trying to, you know what tomorrow's value function is, and let's say that it is in some Banach space. It's a function in some Banach space. And then you're defining today's value function, also some function in a Banach space, hopefully the same Banach space. And then you're mapping to what we're doing is just mapping tomorrow's value function to today's value function. And this is just a mapping in a Banach space. And I say it's a difference equation because there's t plus 1, there's t, and then there's t minus 1, etc. It's just a difference equation in a Banach space. Now, the thing is, this approach can be applied to many things: robust optimization, habits, whatever. Most of these things, when they write it down in a recursive form, they are writing it down now as dynamically, it will be a difference equation in a Banach space. So what we're doing, the computational approach and many of the tools that we're doing can be applied. You just plugged in, we can plug in other aggregators here and push a button and we're ready to go. Stochastic productivity, well, again, we just did some calibration thing. Of course, there's uncertainty about these numbers, but we didn't want to focus on that until we focused on the other uncertainties. Now, how do we solve this computationally? We have the capital stock and the carbon concentrations and the temperature. 6 variables are continuous. You don't want to discretize any of these. However, these other things, which are basically exogenous random variables, are, well, zeta and chi are exogenous. J is a finite state Markov chain, and that's fine to have finite state Markov chain being discretized. We have no reason to prefer continuous versions of J. And so we discretized those 3 dimensions, and with this many time-dependent values. See, by the way, these things are going to depend on time because this system is not a stationary system. It's a non-stationary system. Time 2050 is different from 2030. And so you have to use different thetas at different points in time. And by the way, 90 times 20 is like 1,800 times 16. This is like 25,000 different discrete state variables in those 3 dimensions. And for each one of those theta values, you then have a 6-dimensional continuous function for the value function. Now, and basically then we're doing backwards induction. You take tomorrow's value function, hit it with some operator, and get today's. And now, so what do we have to do? Well, this is just, as I talked about in dynamic programming. At each time t, you have to choose a set of approximation nodes in your state space. We've already done that for the theta of the discretized states. We also now have to do this for the continuous states. Choose a functional form. We have our terminal, and then we just iterate. All this maximizing. You choose the best action you can given the constraints, and then you just maximize this. So basically, but now the nice thing here is that this is highly parallelizable, because for each of these discrete thetas, each of these discrete points that specifies your long run risk state and the J state, for each one of those, you can compute today's value function by solving solving this problem. But the thing is, you can do this for each of those theta vectors separately, because they don't interact. They, there's no, you're not going to be doing any interpolation in that dimension. So basically, you have roughly 25,000 optimization problems here, which can be done independently. And then you gather in all the data from all of that, and then you get you then take that data and then use some regression method or whatever to get your new value function conditional on a discrete theta. This also turns out to be parallelizable, because basically what we did is that as soon as you do the analysis, complete analysis for one theta discrete state, then you turn on the regression. And so you don't have to wait for all the thetas to be done to do this. Now, what makes this problem difficult is that when you look at the range of the capital stock into the future, because the productivity process has this long run risk aspect to it, you've got to solve a dynamic programming problem where in the future, the maximum possible capital stock is 100 times the minimum. So you've got to compute a value function over an enormous range. And what matters is that it's not that it's enormous in absolute sense, it's relative. It's that the top is 100 times as big as the bottom. And given the curvature of most any economics problem, this is a major challenge, because you're going to have major nonlinearity. Also, you're going to have a substantial change in climate state variables. The value function is strongly nonlinear. So what we do is we, in total, when we discretize the thetas, and then we also have to take particular collocation points, if you want to call them that, in the continuous dimensions, we end up having to solve this problem over and over again for a total of 1.5 billion approximation nodes. And we have to solve 372 billion. We had to solve 372 billion optimization problems of that form. And when I saw that number, I was tempted to tell Young Yang to go back and slightly change the problem so that we would have to do 3 times as many optimization problems and make it 1 trillion. But he'd worked so hard on this, I decided not to. But that would have been wonderful if I could say we had 1 trillion optimization problems. 372 billion is still kind of a big number. How could we do this? We did this because we had access to a supercomputer called Blue Waters. And in this run here, this particular one run, we did We grabbed 84,000 cores, and it was done in 8 hours with parallelism. If we didn't, if we had to do it on a laptop without parallel and serial, it would take 77 years. And Young Yang, he's a very impatient guy. He did not want to wait 77 years before he had his 10-year case. So, now, by the way, I will say, by the way, these numbers are all from 2013, I think. Now the speed, so these are, these numbers are 7 years old. Now, also, now I will say this, that by the way, we did some testing. Now, the code operated at about 10% efficiency. That means 10% of peak flops. Now, in the supercomputing world, that is considered good. So we aren't just using, things are not being slow because of communication problems, no. They are at 10% of peak floating point operations, and that is good in the supercomputing world. Also, we did tests on how well they scaled, and this algorithm, you give it twice as many cores and the running time comes down in half. And that's what supercomputer people care about. So we have efficient use of supercomputing power. Now, there's a lot of things that could be done to improve this in terms of the software and a variety of things. We didn't use any GPUs. Basically, Young Yang and I were on our own. And so we didn't have any help from any computer people or computational mathematicians. So we were stuck with what we knew, and now I'm sure others should come along and speed it up. And the next generation machines could have also probably speed this up. Now, what we typically do is that at the end of, for most people, they do that and give the results, and that's it. But now we're going to verify. See, at each step, what we did is, you see, what you do in dynamic programming is you say, okay, I'm going to compute the value function at a number of states. And then I'm going to interpolate over those states, the continuous states. Now, that's not good enough for us. What we then do is we then randomly pick other states and then see what our approximation says is the value. And then we call up the optimizers and then says, okay, what should that value be when you compute solve the optimization problem? And we do the same thing for the controls. And we ask, this gives us a Monte Carlo sampling approach to estimate the error. And what we found is that the value function errors in the L1 norm were less than 10 to the minus 4. And in fact, when you get to earlier years, it's even better. The errors in consumption and emission controls are also 10 to the minus 6 in iterations down here in 2020, 2030, 2040. However, in later years, it was higher, but still basically 3-digit accuracy. Now that's L1, that's the average absolute value of the error. And here, the L infinity, the absolute maximum error. And what we find is that at almost all these iterations, the absolute maximum error was on the order of 10 to the minus 2. So we basically, we clearly had absolute 2-digit accuracy, and on average 3, 4, 5-digit accuracy. So this is what I mean by verification. Every step in this dynamic programming iteration, value function iteration step was tested, and this is the result. So this is something we do, nobody else does. That was one of the innovations of that paper that came out in last December in JPE. We had these verifications. We did these verification tests. What are the results? Well, for the social cost of carbon, this is the number that Nordhaus gets, 37 for his preferred choice of size. So I forget, size is, I think this is what they call risk aversion 2, I guess. Anyway, intertemporal elasticity substitution of 0.5. He gets $37. Now, when he goes to, this is deterministic. When you go to intertemporal elasticity of consumption 2, then you get a much higher number. But it was down here was his preferences. Now, by the way, if you look at the utility function, you find that gamma, the risk aversion parameter, disappears when it's deterministic. All you have is this. However, what happens when we add risk aversion? Well, if you have small size, small intertemporal elasticity of substitution and consumption, you see that adding risk aversion increases the social cost of capital. At the higher end, it decreases. Basically, that log is as constant. As usual, log is a weird case. So, and the paper gives an intuition for why this is happening, and it has to do with the nature of the aggregator. But the key thing here is that our numbers are significantly higher generally than Nordhaus's. So when you add, okay, we didn't get, basically the numbers that he favors are down here, and our numbers are generally higher. When you add risk to this problem, risk in the economy, and I think this is just economic risk, these numbers change. However, they don't become ridiculously, they don't become unbounded. There's still some discipline here. The biggest number is like 100, and the smallest is about 40. So the range here is, pretty good for, we've talking about policy analysis. You can say that, look, whatever your gamma or psi beliefs are, the optimal carbon tax is at least 40. So it has some impact there. We also did a little discounting exercise in the paper, and we found that basically what the optimal policy was doing is discounting the damages from glacier collapse at a much lower rate than it did from direct temperature damages, because this is basically, you see, direct temperature affects output, and so the damage is going to be perfectly correlated to the output. So use the same discount rate, but not with the tipping stuff. Once a damage happens, it's permanent. There's no more fluctuation, so you use a much lower discount rate. Uncertainty quantification. Most economists want calibration. We don't do that. Now, Pindyke has asserted that IAMs create a perception of knowledge which is not there. I agree. That's true, by the way. I don't know why he picks on the climate stuff. Everything, and macro, all that stuff. You get this exaggerated view of what is known, particularly when you take the calibration approach. My response to that criticism is uncertainty quantification. You look at a range of plausible values for parameters, and then you solve the problem for the collection of parameters, and then see how the results are affected by the value of the parameters. So I'm going to do a little four-dimensional example. We don't know what the growth rate is, mean growth rate of the economy is, and so that's going to be capital lambda. And we're going to give 3 values for that. And then also, we don't know what the damage function is. Here's various representations of various damage functions. Here's temperature, and then what the damages are. And these different guys have different opinions about what the damage should be. So what we did is we took the top one and the bottom one, and we let Q to be a damage path, which is just the convex combination of the top and the bottom. So Q equals 0.5 is really just this middle line. And then, and so as you change Q, you just change, it goes up and down. Now, here is uncertainty quantification in 4 dimensions. You've never seen a 4-dimensional graph before, maybe, but this is a 4-dimensional graph. So within each box, I've picked the Q equals 0 means that I picked the bottom damage function in that picture, and I've picked 0.7% as the average annual growth rate of productivity. So for everything in this box, and then in the box, I have utility discount rate changing, and then climate sensitivity, which is a parameter of the climate model. And what do we find? Well, we find that utility discount rate does affect social cost of carbon, particularly then when you add in, if you are at high values of climate sensitivity. Climate sensitivity is basically a measure of how sensitive temperature is to CO2. So what you see is that within this box, social cost of carbon, 40, 80, 150, 250, is very sensitive to discount rate and climate sensitivity. Now, for each of these boxes, you have a different pair of Q and lambda values. And you see that in all of these boxes, boy, the results are sensitive to discount rate and the climate sensitivity. However, when you look across boxes, like let's say this column is where you hold fixed, this first column is where you hold fixed the growth rate at 0.7%, and then you change the damage function from the low damage to the average damage to the higher damage. And you see that you don't get much change. Now here, if you're in high climate sensitivity territory, then you do have a substantial change as you increase the damage function. But at these moderate cases, you don't have much change. Now then we look at what is the impact of economic growth. So as we go from column to column, we go from low economic growth, moderate economic growth, to higher economic growth. Now, does economic growth affect things? Basically, it doesn't look like this doesn't look like it affects things at all. And basically, these boxes, when you go left to right, don't change much. So the specification, what can you conclude from this? The specification for the average growth rate of productivity doesn't really matter. So don't work on making that, tightening up that estimate. The damage function, there is some importance, but it's moderate. And so, yes, you want to spend some time on it, but you know, it's not of first order importance. I mean, basically, the growth rate is not even a second order importance. The damage function isn't of first order importance. What matters are discounting and climate sensitivity. So what this says is that if you want to go forward and improve these things, then you should, on the climate scientist side, pin down climate sensitivity. What is the right climate sensitivity parameter? On the economic side, pin down what the utility discount rate is. So that's from this. And by the way, how do we get this four-dimensional thing? What we did is we solved the problem four dimensions. I think it was about a couple, we chose a couple thousand of these, a couple thousand of points. See, we have a four-dimensional box, Q, lambda, rho, and climate sensitivity. That's a four-dimensional box. We chose about a couple thousand points, carefully chosen according to good approximation theory. And then we took those results for social cost of carbon, then regressed it. And then we did some checking to see if the regression did good in prediction, and it did. And then these are the contour lines from that regression. So we had to take, by the way, this big bad model that took so much time was one where we had not only the economic uncertainty, but also the climate uncertainty, and so that was an enormous problem. I think when you get rid of the tipping part, it goes down. It's much less costly to compute. However, we did it a couple thousand times in order to get this four-dimensional surface, which then tells us what is important and what isn't important. Now, since climate sensitivity is so important, perhaps we should think about treating it as a parameter that we will learn about over time. And that is something that we have done. We haven't written the results up, but we have done some Bayesian analysis. Now, there are other papers that have done Bayesian analysis, but they're nonsense because they have some random variable representing a parameter, but they let the random variable be Gaussian, which means that you know, it can be anything between minus infinity plus infinity. So it's physical. It's nonsense physically. So we basically created a random variable which kept things bounded in a manner that's consistent with beliefs, but allowed us also to use Kalman filtering in order to do the Bayesian updating. And so we got that solved. We did it. Basically, so far the problem is that the current social cost of carbon is not going to be affected much by that. However, the evolution of the social cost of carbon is going to be changed a great deal as you learn as over time you learn the climate sensitivity. Now, the IPCC likes to talk about scenarios, and RCP 8.5 is business as usual. That is, if in Donald Trump's world, we aren't going to really do anything. Now, and so RCP 8.5 predicts this kind of path for temperature. RCP 8.5 is a solid blue line. So that's a solid blue line. It says that temperature will be about 4.6 degrees above pre-industrial levels, and this is all in centigrade, I'm sure, by 2100. But now, all of these economic models that are used in order to generate RCP 8.5 are deterministic. They ignore economic uncertainty. They ignore the fact that we don't know what economic productivity is going to be in the later decades. They assume that they know perfectly what productivity is going to be. What happens is that when you add uncertainty, add our uncertainty to this exercise, you will find that the median path does follow basically exactly what the deterministic analyses say. So our median path does kind of represent what the deterministic model is doing, which kind of makes sense. You think of the stochastic model as being the deterministic model plus some noise, and that's what we have here. Our median does match, our median is a broken red line, does match the deterministic RCP 8.5 path. But look at what happens. This is a 75% quantile. That means that you have a 25% probability of the temperature in 2100 being bigger than 5. And then here's the, let me see, this is the 90% quantile. That means you have a 10% chance of the temperature being above 5.8. And there's a 5% chance of the temperature being above 6. Now, there's also some chance of it being down here too. But you see, the loss function here is very convex. You care a lot more about the damages on the upside than about the world's okay on the downside. The convexity of the convexity means that you care about the worst case scenarios a lot, or the bad case scenarios a lot. So all this discussion about what's likely, what's possible, whatever, is severely biased by only looking at deterministic models. Now, some people argue for a 2-degree target. Now, basically, so we've done that too. We put that into our model and said, okay, suppose you're trying to optimize the present value of utility, but with no particular target imposed, and this is the range of temperatures you get and the social cost of carbon. But now let's say you put in a target, and let's say you put in a penalty term for going above the target, and now what happens is, here's now when you don't put in a target. Now look down here, you put in a target, no target, you put in a target, today's social cost of carbon goes up a bit, but notice that between when you're talking about 2040, it goes up substantially, and then when you're talking about 2090, the range of social cost of carbon goes up greatly. What that means is that if you do have this target, then you're going to want to, in order to have 82% success, you're going to want to plan to have very high social cost of very high optimal taxes, carbon taxes in the latter half of the century. and it gets really bad if you want 100% success. Now, by the way, the thing is the deterministic models, see with deterministic models, what you can do in this 2-degree business is you can say, okay, I'm just going to go up to 2 degrees and stay there. And so what happens is, yeah, they go up to 2 degrees and stay there, and then the social cost of carbon peaks out at about $1,000, which is still quite high. What we show is that, no, if you have uncertainty, you see, and you want to stay below it, you've got to you got to work much harder. And so then the range of cost of carbon is much, much higher. Now, we've since then done, since then, we've also looked at what happens if you have a 2-degree target, but you have direct air capture of carbon. And what we show is that if you have direct air capture technology, see, by the way, the Swiss now have something that they can take CO2 out of the atmosphere for about $600 a ton. And presumably that's going to get better. I know one guy who claims that he's going to get it down to $50 a ton. So what we did is we looked at the following things. Suppose the current cost is $800 per ton of direct air capture, and that it's going to become in each year 2% more efficient. So that after 70 years, you're going to have the cost is going to be $200 a ton. What happens is that you can then attain this target of 2 degrees, but by 2070, 2080, you've got a technology that only costs about $200 per ton of carbon, and that's going to kick in, and that's going to suck out all the CO2 you need in order to meet the 2-degree target. So you see, basically, you don't deploy the technology now when the cost is very high, but when the cost starts at 800 and then declines, and then there's some contingencies, let's say around here, where you do start to deploy the direct air capture cost, and then you get down here and you do it in a big scale. So with direct air capture, using a pessimistic cost and a pessimistic rate of progress, you see that the 2-degree target does become possible. Now, there's a lot we can do with this. I think the main point is that within this one model, we can talk about social cost of carbon. We can talk about how economic uncertainty affects it. We can talk about how tipping point processes in the climate can affect it. We can talk about 2-degree target, direct air capture, all in this one model. And this is, I think, an example that should be followed more generally. Now, I will read these questions. I'm not going to say anybody's name, so I'm going to keep this in the official. Now, one question was, what approximation did you use to interpolate the value function? Now, I may have used the word collocation. That was a mistake. We don't do collocation. We do regression. And that is because we want to have accurate policy functions as well as accurate value functions. So we want to have a good approximation for the derivatives of the value function. So what we have to do is regression. Now, what we did is, I believe it's a polynomial in the log is what we did. And so this took, of course, some testing and trial and error, but we found that the key problem is the capital stock state, and making that its contribution expressed as a polynomial in the log of capital stock, that allowed us to get by with a relatively small number of terms. And so then it was really what I called Chebyshev regression in there. Now, the collocation, the regression points cover an enormous range. And they have to, because you're doing a regression of a highly nonlinear thing over enormous range. by having a functional form being polynomial of the polynomial of the log, you can now handle the curvature over this very long range. So that's what we did. Now, I wanted to finish answering that one technical question. And so thank you for your attention. And let me turn down this. Okay, what do I do here? Yeah. Yeah. Oh, yeah, I want to go back to, okay. So thank you for your attention and for your questions. This is, like I said, this is an example of what could be done, what can be done. And a lot more can be done. And in fact, I find it hard to imagine that there's a paper out there on these matters that couldn't be improved by using this framework. A slightly immodest claim, but by the way, this did get published in JPE, a top journal, and basically none of these other papers are getting published in these top journals. So thank you.